This is SpaceTime Series 27, Episode 57, for broadcast on the 10th of May, 2024. Coming up on SpaceTime, new observations show galaxies evolved much faster than previously thought, how the moon turned itself inside out, and a new crew takes over aboard China's space station. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that starbars found in the centers of many spiral galaxies, including our own Milky Way, indicate that early galaxies evolved much faster than previously thought. The findings, reported in the Journal of the Monthly Notices of the Royal Astronomical Society, look back more than 10 billion years in time, showing how the universe's early galaxies were less chaotic and developed more quickly. Astronomers used the Webb Space Telescope to search for evidence of bar formation when the universe was just a few billion years old. As these elongated strips of stars develop, they regulate star formation within a galaxy, pushing gas into the galaxy's central region. And their presence tells scientists that galaxies have entered a settled, mature phase. Now, previous studies carried out using NASA's Hubble Space Telescope had been able to detect starbars forming in galaxies up to around 8 or 9 billion years ago. But the increased sensitivity and wavelength range offered by Webb means astronomers were able to see the phenomenon happening even further back in time. The new findings mean scientists will have to rethink their theories about galaxy evolution during the early stages of the universe's formation. The study's lead author, Zoe LeConte from Durham University, says galaxies in the early universe are maturing much faster than previously thought, which is a surprise because one would have expected the universe at that stage to be a very turbulent place with lots of collisions between galaxies and a lot of gas that hadn't yet transformed into stars. However, Webb's seeing a lot of these star bars much earlier in the life of the universe, and that means galaxies were far more settled at that stage in their evolution than previously thought. LeConte and colleagues used Webb to look for bar formation in galaxies as they would have been seen between 8 and 11.5 billion years ago. The universe itself is 13.8 billion years old. Now, of the 368 spiral galaxies observed, the authors found that almost 20% of them had starbars. That's twice as many as what was observed by Hubble. And this implies that starbar-driven galaxy evolution has been happening much longer than previously thought. The findings also mean current simulations of the universe will need to be scrutinized to see if astronomers can still get the same results as the observations made by Webb. Still, as astronomers look further back in time and space, they were able to see fewer and fewer starbar-forming galaxies. They say this might be because galaxies at an even earlier stage of the universe's evolution might not have been as well formed. There's also no way currently of seeing shorter bars of stars, which are less easy to spot, even with the increased telescopic power offered by Webb. The authors now want to investigate even more galaxies in the early universe to see if they've also formed starbars. Eventually, they hope to look back some 12.2 billion years to see starbar growth over time and maybe even determine the mechanisms behind it. See, understanding this will also help us better understand the evolution of our own galaxy, which is also a barred spiral. This is SpaceTime. Still to come, how the moon turned itself inside out, and a new crew takes over aboard China's space station. All that and more still to come on SpaceTime. A new study combining computer simulations and spacecraft observations helping to explain the long-standing mystery surrounding the moon's lopsided geology. About 4.5 billion years ago, a small Mars-sized planet called Theia smashed into the early proto-Earth, turning both bodies into a vast magma ocean, which coalesced, eventually solidifying into the Earth we know today. Now, the force of that cataclysmic impact event also flung lots of molten ejecta and debris out into space. Slowly, this debris accreted and coalesced, cooling and solidifying to form the moon. Now, this scenario of how the Earth's moon came to be, known as the giant impact theory, is largely agreed upon by most astronomers. but the minute details of exactly how it happened are still a matter of intense debate. Now, a new study reported in the journal Nature Geoscience offers important fresh insights into the evolution of the lunar interior and consequently the moon as a whole. Most of what's known about the origins of our moon comes from analysis of rock samples collected by the Apollo astronauts more than 50 years ago, and they then combined that with theoretical models. The samples of basaltic lava rocks brought back from the moon show surprisingly high concentrations of titanium. And later satellite observations found that these titanium-rich volcanic rocks are primarily located on the moon's near side. But how and why they got there has remained a mystery until now. Now, because the moon formed fast and hot, it was likely also covered by a global magma ocean. And as the molten rock gradually cooled and solidified, it formed the moon's mantle and bright crust, which we see when we look up at the full moon at night. But deep below the surface, the young moon was still widely out of equilibrium. Models suggest that the last dregs of the magma ocean would have crystallized into dense minerals including ilmenite, a mineral containing titanium and iron. The new study's lead author Weigang Lian from the University of Arizona says that because these heavy materials are denser than the mantle underneath, it creates a gravitational instability, and consequently you'd expect this layer to sink deeper into the moon's interior. Somehow, in the millennia that followed, this dense material did sink into the interior, mixed with the mantle, melted, and then returned to the surface as titanium-rich lava flows, which are detected on the lunar surface today. That means the moon somehow literally turned itself inside out. But there's been very little physical evidence to shed light on the exact sequence of events during this critical phase of lunar history. And there's a lot of disagreement in the details of what actually went down, quite literally. For example, did the material sink as it formed a little at a time, or did it sink all at once after the moon fully solidified? Did it sink into the interior globally and then rise up again on the lunar near side, or did it migrate to the near side from the far side and then sink? Each of these models holds profound implications for the geologic evolution of the moon. Now, previous research predicted that the dense layer of titanium-rich material beneath the crust first migrated to the near side of the moon, possibly triggered by a giant impact on the far side, and then sunk into the interior in a network of sheet-like slabs, cascading into the lunar interior almost like waterfalls. But when that material sank, it left behind a small remnant in a geometric pattern of intersecting linear bodies of dense titanium-rich material beneath the crust. And Liang and colleagues have seen a similar pattern when they examined subtle variations in the moon's gravitational field, revealing a network of dense material lurking below the crust. So, the authors compared simulations of a sinking limonite-rich layer to a set of linear gravitational anomalies detected by NASA's Grail mission. Its two spacecraft orbited the moon in 2011 and 2012, measuring tiny variations in its gravitational pull. These linear anomalies surround a vast dark region of the lunar near side covered by volcanic flows known as mare, Latin for sea. The authors found that the gravity signatures measured by the Grail mission are consistent with ilmenite layer simulations, and that the gravity field can be used to map out the distribution of the ilmenite remnants left after the sinking of the majority of the dense layer. Liang says the analysis shows that the models and data are telling a consistent story. Ilmenite materials migrated to the near side and then sunk into the interior in sheet-like cascades, leaving behind a vestige that causes anomalies in the moon's gravity field today, as seen by Grail. Now, importantly, the linear gravity anomalies are interrupted by the largest and oldest impact basins on the near side of the moon, and therefore must have formed earlier than those impacts. Now, based on these cross-cutting relationships, the authors suggested the ilmenite-rich layer sank prior to 4.22 billion years ago, which is consistent with it contributing to later volcanism seen on the lunar surface. While the detection of lunar gravity anomalies provides evidence for the sinking of a dense layer in the moon's interior and allows for a more precise estimate of how and when the event occurred, what is seen on the lunar surface adds even more intrigue to the story. That's because of the lunar dichotomy, the incredible difference between the moon's near and far sides. See, the moon is fundamentally lopsided, with the near side facing the Earth and especially the dark region known as Oceanus Procellarum being lower in elevation, with a thinner crust largely covered with lava flows and high concentrations of typically rare elements like titanium and thorium. The thicker far side of the moon differs in each of these respects. Somehow, the overturn of the lunar mantle is thought to be related to the unique structure and history of the near-side Procellarum region. But the details of that overturn are also a matter of considerable debate among scientists. This new work helps connect some of those dots between the geophysical evidence for the interior structure of the Moon and computer models of its evolution. For the first time, scientists have physical evidence showing them what was happening in the Moon's interior during a crucial stage in its evolution. This is SpaceTime. Still to come, a new crew takes charge of China's space station, and we explore the constellation Scorpius, the spectacular M6 and M7 open star clusters, and the Eta Aquarids meteor shower produced by Halley's Comet in the May edition of Skywatch. China's Shenzhou 17 taikonauts have returned safely to Earth after spending 6 months aboard Beijing's Tiangong space station. The crew landed near Dongfeng in the Gobi Desert region of Inner Mongolia 9 hours after handing over space station operations to the new Shenzhou 18 crew who had arrived on station several days earlier. The Shenzhou 18 crew docked with the Tianhe core module of the space station a day after launching aboard a Long March 2F rocket from the Jiuquan Satellite Launch Center in northwestern China. Beijing claims the Shenzhou 17 crew conducted 84 experiments in various disciplines such as life sciences, space medicine, and material sciences, and they undertook 2 spacewalks. The Chinese official Xinhua news agency claims the Shenzhou 18 crew will now undertake experiments in basic physics, microgravity, material science, space medicine, life sciences, and technology. And they'll also try to set up an aquarium aboard the space station to raise fish in zero gravity for food. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for the month of May on Skywatch. May is the 5th month of the year in both the Julian and Gregorian calendars. The month was named for the Greek goddess Maya, who was identified with the Roman-era goddess of fertility Bernardia, whose festival was held in May. But I guess more importantly for many of our listeners, May typically marks the start of summer vacation season in the United States and Canada. Let's start our tour of the night skies by looking east, where you'll see the constellation Scorpius the Scorpion. In Greek mythology, the constellation was named after Scorpius, who was sent to Earth by the goddess Gaia in order to slay Orion the Hunter, after he boasted that he could kill all the animals on Earth. Scorpius stung Orion in the shoulder, but Orion's life was spared by Ophiuchus the Healer, and it was placed in the heavens along with Scorpius, who continues to pursue him for eternity. Orion the Hunter has become the hunted forever, with Scorpius rising in the east this time of year to triumphantly chase and defeat Orion, who sets in the west. Meanwhile, Ophiuchus the Healer rises in the east following behind Scorpius to chase and crush him into the earth as the Scorpion sets in the west. And so, this ancient story continues to play out in the heavens year after year. Interestingly, parts of this story predate the Greeks, with Orion known in ancient Egypt as Osiris, the god of the underworld and of regeneration. The brightest star in Scorpius is Alpha Scorpii, or Antares, the scorpion's heart. In ancient Greek, the name Antares means the equal or rival of Mars, the god of war. That's because its golden orange appearance is similar to that of the red planet, and it passes very close to Mars every 780 years. Easily seen with the unaided eye, Antares is some 550 light-years away, but it looks so bright because it's around 57,500 times as luminous as the Sun, and is one of the largest known stars in the universe. Antares is a red supergiant, about 18 times the mass and 883 times the diameter of the Sun. Were it placed where the Sun is in our solar system, it would engulf all the terrestrial planets, Mercury, Venus, Earth, and Mars, and its visible surface would extend almost as far out as Jupiter. A light year is about 10 trillion kilometers. The distance a photon can travel in a year at 300,000 kilometers per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Astronomers believe Antares began life around 12 million years ago as a spectral type O or B blue star. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish yellow stars, spectral type G yellow stars, that's where our sun fits in. Then there's spectral type K orange stars, and the coolest and least massive stars are known as spectral type M red stars. Each spectral classification system can also be subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest. And then you add a Roman numeral to represent luminosity. So put it all together and you can describe our Sun as being a G2V or G25 yellow dwarf star, one of millions spread across our galaxy. Also included in the stellar classification system are spectral types L, T, and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are about 75 to 80 times the mass of Jupiter, or 0.08 solar masses. Like the similar-sized red giant Betelgeuse in the constellation Orion, Antares will almost certainly end its life as a spectacular Type 2 or core collapse supernova, probably sometime within the next 100,000 years or so. When it does explode, it'll appear as bright as the full moon for several months on end, and will be clearly visible during daylight hours here on Earth. Antares has a companion star, Antares B, located between 224 and 529 astronomical units away from the primary. An astronomical unit is the average distance between the Earth and the Sun, which is about 150 million kilometers or 8.3 light minutes. Spectral analysis of Antares B indicates it's pulling a lot of material off its bloated red supergiant companion. Located near Antares is the M4 globular cluster. Globular clusters are tight balls densely packed with thousands to millions of stars, which were either all originally formed at the same time from the collapse of the same molecular gas and dust cloud, or alternatively, they're galactic centers, the remains of ancient galaxies that have been merged into the Milky Way galaxy over billions of years. M4 is composed of 1 million or so stars originally born some 12 billion years ago. The M4 globular cluster is located some 7,200 light-years away, making it one of the nearest globular clusters to Earth. Easily seen through a pair of small binoculars, it covers an area of the sky as seen from Earth as big as the full moon. Astronomers estimate there are some 150 or so globular clusters orbiting in the halo of the Milky Way. Located near the tail of the Scorpion are 2 open star clusters known as M6 and M7. Open star clusters are loosely bound groups of a few thousand stars, which were all originally formed from the same molecular gas and dust cloud at the same time, but are not as densely bound as globular clusters. Open clusters generally survive for a few 100 million years, with the most massive ones surviving for maybe a few billion years. Now, in contrast, the far more massive globular clusters exert far stronger gravitational attraction on their members, which is why they can survive so much longer. M6, which is also known as the butterfly cluster, is some 12 light-years across and located about 1,600 light-years away. It contains around 80 stars, which are all less than 100 million years old, which is quite young in cosmic terms. The M7 or Ptolemy cluster is named after the famous Greek astronomer and mathematician Claudius Ptolemy. It's about 980 light-years away and is far more dispersed than M6, covering an area around 25 light-years across. And at around 200 million years, it's about twice as old. By the way, the M in terms like M4, M6 and M7 are abbreviations for Messier, in honor of the 18th century French astronomer Charles Messier, who developed an astronomical catalogue of fuzzy nebulous objects in the skies. See, Messier was a comet hunter, and he compiled a list of 103 fuzzy objects which weren't comets, and so from his perspective could be ignored. Later, other astronomers added additional celestial objects to the list, bringing the present catalogue up to 110. Our solar system, in fact most of the stars we see when we look up in the night sky, are located in the Milky Way galaxy's Orion Arm. The Orion Arm, also known as the Orion Spur or the Orion Cygnus Arm, depending on which name you prefer, is some 3,500 light-years wide and around 10,000 light-years long. The Orion Arm is named after the Orion constellation, which is one of the most prominent constellations in the Southern Hemisphere summer and Northern Hemisphere winter. Some of the brightest and most famous celestial objects in the constellation include Betelgeuse, Rigel, the stars of the Orion Belt, and the Orion Nebula, all located within the Orion Arm. The Orion Arm is located between the Carina-Sagittarius Arm, which is more towards the galactic center from our position, and the Perseus Arm, which is more towards the outer edge of the galaxy from our point of view. The Perseus Arm is one of the two major arms of the Milky Way, the other being the Scutum Centaurus Arm. Long thought of as a minor structure, a spur if you will, between the two longer adjacent arms, Perseus and Carina-Sagittarius, evidence was presented in mid-2013 that the Orion Arm might actually be a branch of the Perseus Arm, or possibly a completely independent arm segment itself. Within the Orion Arm, our solar system, the Sun, the Earth, and all the other planets we know are located close to the inner rim in what's known as the local bubble, about halfway along the Orion Arm's length, approximately 26,000 light-years from the galactic center. The local bubble is a cavity in the interstellar medium in the Orion Arm, containing among other things the local interstellar cloud which contains our solar system, and the G-cloud. It's at least 300 light-years across, and it has a neutral hydrogen density of just 0.05 atoms per cubic centimetre. That's just 1/10 of the average for the interstellar medium across the Milky Way, and about 1/6 that of the local interstellar cloud. The hot diffuse gas in the local bubble emits X-rays and is the result of a supernova that exploded sometime during the past 10 to 20 million years. It was once thought that the most likely candidate for the remains of this supernova was Geminga, a pulsar in the constellation Gemini. However, later it was suggested that multiple supernovae in a subgroup B1 of the Pleiades moving group was more likely responsible, becoming a remnant supershell. Our solar system has been travelling through this region of space occupied by the local bubble for the last 5 to 10 million years. Its current location is in what's known as the local interstellar cloud, a minor region of slightly denser material within the bubble. The cloud formed when the local bubble and another bubble called the Loop 1 bubble met. Gas within the local interstellar cloud has a density of about 0.3 atoms per cubic centimetre. From what we can tell, the local bubble isn't spherical, but seems to be narrower in the galactic plane, becoming somewhat egg-shaped or elliptical, and may even become wider above and below the galactic plane, becoming shaped more like an hourglass. And it's not alone, it's abutting other bubbles of lesser dense interstellar medium, including the Loop 1 bubble. The Loop 1 bubble was created by supernovae and stellar winds in the Scorpius-Centaurus association some 500 light-years from the Sun. The Loop 1 bubble also contains the star Antares that we spoke about earlier. Astronomers have identified several, well, I guess you'd call them tunnels, which connect the cavities of the local bubble with that of the Loop 1 bubble. Collectively, they've been referred to as the Lupus Tunnel. Other bubbles which are adjacent to our local bubble are known as the Loop 2 bubble and the Loop 3 bubble. Looks like astronomers still have a problem when it comes to thinking up cool names. Also visible this month is the Eta Aquarids meteor shower, which is generated as the Earth passes through the dust and debris trail left behind by Halley's Comet. Comet P1 Halley's a well-known short-period comet which visits the inner solar system every 75 to 76 years. The 15-kilometre wide mountain of rock and ice will make its next close-up appearance in 2061. It's named in honour of the British astronomer Edmund Halley, who in 1705, after examining ancient Chinese, Babylonian and medieval European records, successfully predicted its return in 1758. However, he died in 1742, before his prediction could be confirmed. The comet's highly elliptical and elongated orbit takes it from between the orbits of Mercury and Venus out almost as far as the orbit of Pluto. Halley's orbit is in retrograde, meaning it orbits the Sun in the opposite direction to the planets, that is, clockwise from above the Sun's northern pole. This retrograde orbit results in it having one of the highest velocities relative to the Earth of any object in the solar system, traveling at some 70.56 kilometers per second, or if you prefer, 254,016 kilometers per hour. As well as the Eto-Acrids meteor shower every May, Halley's Comet also produces the Orionids meteor shower in late October. Astronomers think Comet Halley was originally a long-period comet which took thousands of years to travel to the inner solar system from the Oort cloud, but was gravitationally perturbed into its current orbit by close encounters with the giant outer planets. The Oort cloud is a hypothetical sphere of comets and asteroids beyond the heliosphere, a mixture of vagabonds from the solar system and objects from deep space which have been collected by the Sun's gravitational pull. Occasionally, as the Sun passes by another star, an Oort cloud object will get perturbed and be flung towards the inner solar system. The Eto-Acrids meteor shower runs from the 19th of April through to the 28th of May, peaking around May the 5th, with around 55 meteors an hour, making it one of the Southern Hemisphere's best celestial showers. However, back in 1975, they were running 95 meteors an hour, and in 1980, it was up to 110. Even better, the bright yellow meteors often appear as streaks known as trains. As their name suggests, they radiate out from the direction of the constellation Aquarius and the star Eta Aquarii. Just look towards the east after midnight and before dawn for the best view. And now with the rest of May's Skywatch, we're joined by Jonathan Nally from Sky and Telescope magazine.
G'day, Stuart. Well, where I live at least, daylight savings is over now. We're heading towards winter, so the nights are getting longer, which is good for stargazing. It's actually a really good time for stargazing this time of the year if you live in the Southern Hemisphere. I can't speak for our friends in the north, but for us down here, it's really good because there are lots of great southern-only constellations visible, the ones that we can only see down here. So we've got the Southern Cross for a start. It's just standing upright and really high up in the south, in the middle part of the evening. You just can't miss it. At other times in the year, it's down lower on the horizon and it might get blocked out by trees or houses or something. But at the moment, it's really high up in the sky. To its left are two bright stars, the two brightest stars of the constellation Centaurus. Astronomers call them the two pointers because if you draw a line through them and keep the line going, it more or less points towards the Southern Cross if you're having trouble finding the Southern Cross. Now, if you have good dark skies and you can see the Milky Way, which unfortunately most people in cities can't, see if you can spot the large dark area near the Southern Cross. This is a huge cloud of interstellar gas and dust called the coal sack. Good name for it, the coal sack, because it's just this big dark-looking patch in the Milky Way. And that's because it's a big interstellar cloud, as I said, and it's just blocking out the light of the stars that are behind it. So it's in front of the background stars, if that makes any sense. I'm sure it does. To the right of the Southern Cross, as we look down to the south, you've got these fantastic constellations called Carina, Vela, and Puppis, which most people have never heard of, but they're really good and they're full of fantastic things to see, even just with a pair of binoculars. You get a pair of binoculars and just sweep through this area with them and you can see all these star clusters and you can make out a few nebulae. Just if you use what's called averted vision, don't look directly at it, look out of the side of your eye, and that means that the light is falling on the part of your retina that's better for night viewing than the middle part of your retina, which is better for day viewing. And if you've got a small telescope even, or if you get hold of one, or a friend's got one, or next door neighbour, it's even better. You get a fantastic view of the Milky Way through there. Now, if you get hold of a star chart or maybe an astronomy app on your phone, see if you can find two things particularly. One's called Omega Centauri, which is an enormous, what they call globular star cluster. And there's another one, it's a galaxy called NGC 5128. Very imaginative. Some people call it Centaurus A, and Centaurus A and NGC 5128 are basically the same object, but I was taken to task once by an astronomer because NGC 5128 is the catalogue number of the galaxy. Centaurus A is the name given to the source of radio waves coming out of this galaxy because it's emitting lots of radio waves. When they were first doing first maps of the night sky at radio wavelengths, this is one of the things that really stood out, this thing called Centaurus A, and then they matched it with this galaxy. So if you have dark skies, untouched by light pollution, you should be able to spot these two things even with the naked eye. Just little fuzzy blobs. They're not point like a star. They're like little fuzzy blobs. But then if you get a telescope onto them, then you can see what they really are. Okay, because the eye is not good enough to make out any of the detail in them. What else have we got? Over in the west, just after the sun has set, you can see the constellation Orion, the Hunter, also setting. Nearby, we've got Sirius, the brightest star in the night sky, and brightest star in the constellation Canis Major, or the Greater Dog. A little bit to the north of Sirius, we've got another star called Procyon, which is the brightest star in Canis Minor, the Lesser Dog. There are two dog constellations up there, sort of right next to each other. Down in the southwest, we've got another bright star called Canopus, which is the second brightest star in the night sky. You can really only see that one this time of year, at least from the southern hemisphere. Now, a lot of people don't realise that many of the stars, we've just been talking about brightest stars, right? So many people don't realise that many of the stars they see in the night sky are not single stars. They are actually multiple star systems with 2, 3, 4, some of them have got 6 stars, all very closely bound to one another.
Yeah, our sun's a bit of an outlier like that in being a solo star. Most systems in the Milky Way and elsewhere, I guess, in the universe are multiple systems.
Multiple systems, exactly right. So our sun's on its own, but so many stars out there are multiples. But when you look up in the night sky just with your own eyes, you can't see that. You can't detect that some of these stars are multiple stars. So, for instance, I mentioned Alpha Centauri, which is one of the stars of the two pointers. When you look through a telescope at Alpha Centauri, even a small backyard telescope, you can see that it's 2 stars. You just look with your own eyes, it's 1 star, but look through a telescope and it's 2 stars. So that's very, very common. There's even a third star in that system called Proxima Centauri, but it's much harder to spot as it's very, very faint and a fair distance away from the other two. Most people sort of really wouldn't have a chance of seeing that. You've really got to know where you're looking and what you're looking for. But Alpha Centauri is a classic example of the brightest star in the constellation, but it's actually 2 stars. And that's very, very common up there. Looking at the eastern sky, the other half of the sky during mid-evening, we've got the constellation Scorpius just beginning to poke its nose up over the horizon. Well, it's shouldn't say its nose, its stinger and its claws. It's poking those up over the horizon. And as the night progresses and the Earth turns a bit more, we'll see the full constellation coming up and becoming visible. For us in the south here, that's a good sign that winter's just around the corner. For our friends in the north, it's a good sign that summer is just around the corner. And as the Earth turns even a bit more, as the night progresses, after Scorpius has come up, it's going to be followed by this constellation Sagittarius. Now, like most constellations, the star pattern of Sagittarius really looks nothing like what it's supposed to represent, which is an archer. Right? Most constellations up there just don't look anything like what their mythology or their name suggests. I mean, there's a constellation called Triangulum, which is a triangle, which is just 3 stars joined together. That's really quite easy. But Scorpius actually does have the shape of a scorpion. It really is quite amazing. When you do the join the dots thing between the stars, it really does look like a scorpion, and it stands out so well. It really is quite spectacular. Other spectacular constellations like, say, Orion, can't really see a person there, but if you join the dots and add a bit more, you can get a person. The Southern Cross is quite obviously a cross. There are a few other ones that are similar to their namesakes, but I think Scorpius is probably the best of them all. Now let's look at the planets. Jupiter, which has been nice and bright above the western horizon after sunset, unfortunately now is too close to the sun to be seen. It'll be back in our skies, in our morning skies, in mid to late June. And like Jupiter, Venus too is too close to the sun to be seen at the moment, so we're going to have to give that one a miss for this month. The other 3 bright planets are all to be seen rising above the eastern horizon in the early hours of the morning. So you've got to be getting up early or staying up very late or be some sort of night owl in order to see these, because Saturn is rising just after 2 a.m. at the start of May. Mars follows up over the horizon about a little over an hour later, and then Mercury a little over an hour after Mars. So sort of one after the other, about an hour apart. Now, the good thing this month is that if you have trouble identifying which are the planets, for these 3 planets in particular, it's going to be easy this month because you're going to be able to use the moon to help you identify them. That's because as the moon goes along in its orbit, it sort of passes, from our perspective, from our point of view, our line of sight, the moon sort of passes by each of the planets in a row as it goes around the night sky in its 4-week cycle. And that, Stuart, is the night sky for May.
That's Jonathan Nally from Sky and Telescope magazine, and this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday, and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.